All right, so now we're going to start talking about analyzing graphs. And I thought it'd be really pretty important to have some basic graphs kind of in mind as we get started. And really, we're going to spend like the next 3 sections doing things with graphs. So this will be important. Here we have y is equal to x squared. You'll notice the nice basic parabola shape. It's smooth. It's like a U. It's not pointy like a V. We have y equals x cubed, which starts low and ends high, and it's kind of like a parabola if you took one side of it and flipped it upside down. Similar, anyway. Here we have y is equal to the absolute value of x. You'll notice the nice V shape. This is very pointy. And then finally, y is equal to the square root of x. On this one, notice that there's nothing over here on the left-hand side of the graph. That's because if you take the square root of a negative number, you do not get a real number. Okay, those are complex numbers. We'll look at those in chapter 3 just a little bit. But so when we graph it, we only get a graph on the right-hand side of the graph. So those are some basic graphs. In this section, we're going to look at symmetry, even and odd functions, and then we're going to do something called average rate of change in the difference quotient. And so those will be things to look forward to here in just a little bit. But let's get started with symmetry. Okay, so here we have our first 2 kinds of symmetry. There are 3. We have x-axis symmetry, and it's important to note that with x-axis symmetry, any graph that has x-axis symmetry is not going to be a function, and we'll see why. The reason is because what it means to have x-axis symmetry is anytime you have one point on your graph, you have to have a point with the opposite y value, same x and opposite y value, also on the graph. Well, what do you have? You have one x value right here that gives you 2 y values. And remember, that can't be a function, right? Each input can only have one output. So x-axis symmetry is the least interesting bit of symmetry that we have because these are never functions. The second kind of symmetry that we have is y-axis symmetry. This is way more useful and interesting to us. These kinds of functions are what we call even functions, and we'll see why here in just a second. So with y-axis symmetry, what it means is anytime you have a point x, y, you have to have the opposite of x, y on the graph. Now this is a function, right? This doesn't blow up the ability to have a function. We have the same y values, but that's not a problem. Remember, each input only has one output. It doesn't go back the other way. And what we say for even functions that have this kind of symmetry is that we know it works or we know that we have an even function if f of negative x, so if you plug in the opposite of x, is equal to f of x. And so I actually have an example. Show that f of x equals 2x to the 4th minus x squared is even. And so for these kinds of problems, it's not enough to show that if you plug in 2 and negative 2 that you get the same thing, because all you've done is prove it for 2 and negative 2. We have to show it for every possible value of x. So what do? We plug in negative x. We want to show that f of negative x is equal to f of x. So if I plug in negative x, I'm going to be really careful with my parentheses because negatives are goofy and will mess things up if you're not careful. But what happens when you raise a negative to an even power? Well, the answer is the negative drops out. It goes away, it turns it back into a positive. So my negative x raised to the 4th is the same as x to the 4th. My negative x squared is the same as x squared. Notice this minus sign was what we started with, and it's just kind of floating through the problem. So we end up with 2x to the 4th minus x squared. That is a 2, I promise. And that's the original function. And so we showed that f of negative x and f of x are exactly the same thing. That's what it means to be an even function. All right, we're going to clear the board and do some more. All right, so here is our last kind of symmetry, origin symmetry. Okay, this is a rotational symmetry, so we're, think of things spinning, bicycle wheels, pinwheels, windmills, things that spin. These are what we call odd functions. And so here we go. What it means to have origin symmetry is that if you have the point x, y on the graph, the opposite of x, opposite of y is also on the graph. So we've changed both signs. Now, in terms of function notation, what that means is this. An odd function is when f of the opposite of x is equal to the opposite of f of x. So now when you plug in a negative, you get the opposite of what you would get if you plugged in a positive. So again, we want to show that, and I have a function here, f of x is equal to 6x cubed minus 7x is odd. And so what we're looking to show is that when we plug in negative x, then we end up with the opposite of what we started with. So I plug in my negative x, we get negative x to the third here and just a negative x there. But what happens when you raise a negative to an odd power? You get another negative. And so I can pull that negative out front and just call it a negative 6 and change this one from a minus 7 to a plus 7. Okay, it's real easy to see it right here, right? You can't get rid of that negative. It actually just changes the sign. Well, at that point, it looks kind of similar to what we have, except we have opposites. So to finish showing it, we just pull that opposite out. So if I divide them both by negative 1 and pull that out front, I have 6x cubed minus 7x, and there we go. We have the opposite of f of x. So if you're asked to show that you have odd functions, that's how you want to go about doing it. All right, so we have a couple more things here in this section, and I'm really pretty excited about them. They're pretty fun, so let's get started. Okay, so we have two things left to look at. They're really the same thing, just kind of presented a little bit differently. So we're going to look first at average rate of change. An average rate of change just measures how much something changes over a given interval. So in terms of a graph, what we're looking at is you have two x values, x1 and x2, and those x values have function values that go along with them, right? They have a y value each connected to them. And so the average rate of change is just the slope between 2 points. Well, how do you find the slope? It's rise over run, y2 minus y1 over x2 minus x1, or in function notation, f of x2 minus f of x1 all over x2 minus x1. So you'll see here I have an example. I want to find the average rate of change on the interval from -1 to 3. Now, importantly, these are my x values. I'm going to use -1 to be x1 and 3 to be x2. Then I need my function values, right? I need the y values that go with those. So I plug in -1 and I plug in 3. If I do, I get -7 when I plug in -1. I get -23 when I plug in 3. And so then I just set up my fraction. F of x2, so the -23, minus, be really careful with the signs. Those minus signs and negatives, they're a really easy place to make mistakes. So please be careful. So minus -7, that gives me -16 on the top. And on the bottom, 3 minus -1 gives me 4. And so I get an average rate of change here of -4. And that's really just the slope of a line connecting those 2 points. Okay, we call it an average rate of change because obviously my function here is not exactly following that line. But on the average, this is the change that happens from one point to another. And so it's just kind of averaged out. And that's average rate of change. We have one more thing to look at, and I'll get it on the board. All right, so here's the last thing that we have. It's called a difference quotient. And it really is exactly the same as an average rate of change. It's just presented a little bit differently. The reason we have this and the reason it's presented differently is because this is going to be a really important concept when you get to calculus. Okay, so if you're not planning on taking calculus, I'm sorry, you're just going to have to do it. If you are planning on taking calculus, this is going to be one of the first things you spend a lot of time with when you get there. All right, so the difference quotient is f of x plus h minus f of x all over h. And so what we have is it really amounts to the same thing, except that instead of starting at x1, we're starting at some just x value. And then we're adding h on, and so that moves us over to x plus h for that second x coordinate. And so you'll notice I still have 2 points, one for f of x, one for f of x plus h, and this is still really the slope, because if you subtract your x values at the bottom, x plus h minus x would just give you the h. So yeah, sit with it a little bit, ponder it, think about it, work it through in your own head, but it really is the same as the average rate of change that we looked at before. Okay, so here's how we might use the difference quotient. And this is going to be big and a little bit messy at times, so be careful. Go back and watch this video a few times and make sure you know what you're doing. All right, so I want to find the difference quotient for f of x equal to 2x squared minus 3. So before I jump in to using this formula, I want to notice something. I have f of x, right? That's what I just gave us, the 2x squared minus 3. H, it's just h. It's just this random, very little number usually. And it's never something we know. We just call it h. What I need is f of x plus h. So you'll notice the first thing I did here was I plugged in x plus h into my function so that I could come up with an expression for f of x plus h, which I then put here at the very beginning of my fraction. So let's kind of walk through this a little bit. So I plug in x plus h, so I have 2 times x plus h squared minus 3. I squared this out. Please remember, you can't square just the two pieces. You have to actually multiply x plus h times itself. But anyway, if you do that, you get x squared plus 2xh plus h squared, and I distributed the 2. Okay, so that's where all that came from. Again, feel free to go back and watch this again. So I put that here where the f of x plus h is in the formula. I then put a minus with the f of x. Be really careful, put it in parentheses. That way you'll remember to distribute the minus sign. And what you'll notice is I have a 2x squared here, and then over here I have a minus 2x squared. So those go away. You'll notice they didn't make it down to the next line. The same thing happens with the minus 3. I have a minus 3 here, then I have a subtraction sign and a minus 3 there. Those are again going to knock each other out. And so I'm really just left with 4xh plus 2h squared all over h. Everything on the top has an h. That's important. If you don't have h and everything on top, you probably did something wrong. Okay, so go back and try and figure that out. So I factor out the h, which then allows it to cancel on the bottom and leaves me with 4x plus 2h, which is my difference quotient. So the way this is going to transition into calculus when you get there, for those of you who plan on taking calculus, is that we're going to make h get incredibly little. We're going to do what's called taking a limit as h gets very, very, very tiny. And you can't divide by 0. That's bad, right? So it's the first really important concept in calculus, taking a limit, and this is a big part of it. So there you go.